Hello everyone, my name is Amin Fakhari and today I will be talking about our paper Motion and Force Planning for Manipulating Heavy Objects by Pivoting. This is joint work with Aditya Patankar and Dr. Nilanjan Chakraborty. Manipulation of heavy and bulky objects is a challenging task for manipulators and humanoid robots. An object is considered heavy if the manipulator's joint torques are not large enough to balance the object weight while lifting it off the ground. Therefore, heavy objects cannot be manipulated with the usual pick-and-place strategy due to actuator saturation. Consider the manipulation scenario shown in this figure, where a heavy object has to be moved from an initial pose to a final pose by a dual-armed robot. The object has to negotiate a step during the manipulation, while it implies that the final pose cannot be achieved by either pick-and-place strategy or by pushing. One possible way to move the object and negotiate the step is to use a sequence of pivoting motions, which we call object gating. Object gating is a common strategy used by humans to manipulate heavy objects like furniture. Therefore, the goal of this paper is to develop an algorithmic method to compute a plan for manipulating heavy objects by a sequence of pivoting motions. Consider a heavy object being moved by using n manipulators from an initial pose CO to a final pose CF in SE3, while maintaining a point or line contact with environment. Let phi I be joint a space of manipulator I and EI be pose of the end effector of the manipulator I in SE3. Therefore, the relation between phi I and EI is determined by the manipulator forward kinematics map, which is Fk. Our plan for pivoting operations consists of motion plan and force plan. Our motion planning problem is defined as computing a sequence of joint angles phi I to manipulate the object while maintaining point or line contact with the environment from its initial pose CO to a final pose CF when initial configuration and pose of the manipulators are given. Note that the point contact acts like a spherical joint and a line contact acts like a revolute joint. We assume that there is no relative slippage at the contact interfaces. The motion is quasi-static and the object always remains in the manipulator's workspace. Our force planning problem is computing a sequence of joint torques corresponding to the minimum contact wrenches required to be applied to the object during the manipulation. In this paper, we will focus on the motion planning problem. We have studied the force planning problem for a given motion plan in our recent paper, and we will combine it with our motion plan to generate torques to achieve the motion. Pivoting was first introduced by Ayama as a new method of non-prehensile manipulation. Based on this method, Yoshida developed a motion planner for a humanoid robot for manipulating bulky objects by pivoting. However, this method is limited to motion on rods and shape curves to satisfy non-holonomic constraints, which is not always required. Therefore, they propose a general gate planning method as an optimization problem by defining the intermediate poses and using a screw linear interpolation to manipulate the object by gating between any two arbitrary poses. The key challenge in solving the motion planning problem is that the kinematic constraints of the object maintaining a point or line contact with the ground during the motion corresponds to nonlinear manifold constraints in the joint space of the manipulator. In sampling-based motion planning in joint space, these constraints are very hard to deal with. In this paper, we present a novel two-step task space-based approach for motion planning. In the first step, we develop an algorithm to compute a sequence of intermediate poses for the object to go from the initial pose to the final pose. Every two consecutive intermediate poses implicitly determine a point or line on the object and the environment which stays fixed during the motion. In the second step, we use a screw linear interpolation to determine a task space path between two intermediate poses aligned with resolved motion rate control to convert the task space path to a joint space path. In this paper, we use dual quaternion representation of the object and end effector poses for motion planning. Using dual quaternions is computationally more efficient compared with using transformation matrices. Quaternions are the set of hypercomplex numbers. The quaternion Q can be represented as a four-tuple where Q0 is the real scalar part and QR is the imaginary part. The quaternion Q is a unit quaternion if norm of Q equals to 1. The unit quaternions can be used to represent the set of all rigid body rotations, which is SO3. Here, L is a unit axis and theta varies between 0 and pi. Dual quaternion D is defined as D equals P plus epsilon Q, where P and Q are quaternions and epsilon is dual unit. D is a unit dual quaternion if norm of D equals to 1. The unit dual quaternions can be used to represent the group of rigid body displacement, which is SE3. Here, QR is the unit quaternion corresponding to rotation, and QP corresponds to the translation. Chasles-Mosey theorem states that the general Euclidean displacement of a rigid body can be expressed as a rotation theta about a fixed axis S, which is called a screw axis, and a translation D along that axis. The screw parameters are defined as L, M, theta, and D, where L and M are called Plucker coordinates. The screw displacement can be expressed by the dual quaternions as dt, where phi is dual number and L is a dual vector. In general, there are three primitive motions to manipulate an object while maintaining contact with environment: rolling, sliding, and pivoting. All other motions can be made by combining these three primitive motions. Manipulation by sliding can be useful in many scenarios, like picking a penny off a table. However, in heavy and bulky object manipulation scenarios, sliding may not give feasible solutions. Therefore, in this paper, we will focus on manipulation using pivoting primitive. Pivoting is a motion where an object is moved while maintaining a point or line contact with a support surface. A point contact acts like a spherical joint, and motion of the object is restricted to SO3. A line contact acts like a revolute joint, and motion of the object is restricted to SO2. Suppose an object can reach a goal pose from a start pose using a single pivoting motion. This can happen when the start and goal poses are such that there is a common vertex between these poses. There are three popular choices for interpolation between two given poses using unit quaternion representation of orientation: linear interpolation for both orientation and position, spherical linear interpolation for orientation and linear interpolation for position, and screw linear interpolation. As you see, by using the first two approaches, the object will penetrate the support surface so that the motion plan will not be visible. However, screw linear interpolation ensures that all the intermediate poses will have a point or line fixed to the support surface in common, and therefore the non-penetration constraints of the object with the support surface is automatically satisfied without explicitly enforcing it. Screw linear interpolation is a 1 degree of freedom smooth screw motion with a constant rotation and translation rate between two object poses in SE3. It's coordinate invariant and provides a straight line in SE3, which is the shortest path between two given poses in SE3. The joint space path that we compute aligned with the object path using a screw linear interpolation automatically satisfies all the task-related kinematic constraints, without any additional explicit representation of the contact constraints. Moreover, when using multiple manipulators to pivot an object, the motion of each end effector can be obtained independently by using a screw linear interpolation using a shared interpolation parameter. This will ensure that the closed chain constraints formed by the manipulator and the object is maintained throughout the whole motion without explicitly encoding it. In order to manipulate an object between any two given poses while maintaining contact with the environment, multiple pivoting moves can be combined by defining a set of appropriate intermediate poses. The set of the intermediate poses Ci are defined in a way that the motion between any two successive poses can be represented by a single constant screw pivoting motion. Therefore, we can conveniently represent the motion between any two given object poses by using screw linear interpolation to ensure that the object maintains in contact with the environment continuously. Object gating consists of a sequence of intermediate poses. Here, three successive intermediate poses while pivoting about the vertices A and B are shown. In order to manipulate the object from an initial pose to a final pose by object gating, a sequence of rotation angles alpha between these two poses, as shown in these figures, should be properly determined. We can find alpha by using an optimization problem, as you see here. The objective function is the norm of the vector alpha. The first and second constraints represent the relative distance and angle between the initial and final poses, and the last constraint is used to limit the maximum allowed rotation angle due to manipulators' limitations. Note that in order to find the feasible number of edge contacts, we need to repeat the optimization problem from k equals to 1 until the first feasible integer number. In order to find the joint angles of the manipulators in the joint space, we use the weighted pseudo-inverse of the manipulator Jacobian. In this equation, phi t is the vector of joint angles at step t, xt is the vector of end effectors poses at step t, j is pseudo-inverse of the manipulator Jacobian, and lambda is the step length parameter. Our manipulation strategy can be summarized as follows. First, we compute a sequence of intermediate poses for the object to manipulate from the initial pose to the final pose in task space. Based on that, we compute the end effector poses for each object intermediate pose. Then, we use a screw-linear interpolation for each of these end effector poses individually with a shared screw parameter to determine a task space path in SE3. And then, we map from task space to joint space to find the joint angles of the manipulators. Finally, we compute the minimum required contact ranges and the corresponding manipulators' joint torques required for object manipulation. Note that these steps can be done either sequentially or they can be interleaved in a single discrete time step. Here, you see examples of manipulating a cuboid by a sequence of vertex and edge contacts when two adjacent or opposite object faces are in contact with the environment in initial and final poses. And here, you see an example of manipulating a cylinder by a sequence of point and face contacts. Note that our proposed gate planning method can be applied to complex shaped objects. This example shows motion planning for reorienting a heavy object from an initial pose to a final pose by object gating. As you see, by using the proposed optimization problem, we can find the minimum number of contact edges, or alpha, required to reorient the object between these two poses. In this example, we demonstrate our motion and force planning approach for manipulating a heavy cuboid over a step by both 7 degrees of freedom arms of the Baxter robot. As you see, computed motion plan includes 3 stages: pivoting about the object edge, pivoting about the object vertex, and pivoting about the step edge. Note that in stage 3, we change the end effector contact locations before pivoting the object about the step edge. The variations of the normal contact forces and also joint angles in the right and left arms of the Baxter robot are shown. In this paper, we showed that a sequence of pivoting motions can be used for manipulating heavy objects. Pivoting motions can be mathematically modeled by means of screw-linear interpolation in SE3. Screw-linear interpolation automatically satisfies all the kinematic and task-related constraints of the pivoting motion without explicitly encoding them. We also showed that by defining appropriate intermediate poses by using gate planning, we can manipulate the object between any two given poses by a sequence of pivoting motions. Finally, our proposed motion plan can be combined with a second-order cone programming-based approach to compute the joint torques and grasping forces. Our future work includes the relaxation of the quasi-static assumption for the force planning and experimental evaluation of the proposed approach. Thank you for your attention.